Welcome to this explainer. Today, we're going to demystify the hidden scaffolding of the digital world, the stuff that makes massive software run without, completely crashing. Have you ever wondered what's actually happening under the hood when you use your favorite apps? Like how they handle millions of requests without even breaking a sweat? Well, let's dive in and find out. Okay, to really get this, let's think about a real-world problem. How does your computer organize and search millions of global flight paths so incredibly fast? Seriously, when you book a trip from New York to Tokyo, the reservation system sifts through countless connecting airports, ticket prices, routes, and it hands you the cheapest itinerary in literal milliseconds. How is that level of efficiency even possible? To answer that, we'll be covering 5 main topics in this explainer. First, the anatomy of data. Second, linear versus nonlinear structures. Third, the rules of algorithms. Fourth, measuring algorithm efficiency. And finally, the big O notation. All right, let's kick things off with section 1, the anatomy of data, the raw material. So when we're organizing our digital warehouse, data rarely exists in a vacuum, right? A data structure is the structural representation of the logical relationship between data elements. Basically, it's used to manage data flow and drastically increase the efficiency of a program. Think of a student record at a university. A data structure links their ID, name, grade level, and GPA into one organized, highly efficient custom package rather than just leaving it as this chaotic pile of floating numbers. It guarantees we use memory properly and speeds up processing time. But before we can actually code these structures, we need a blueprint. And this is called an abstract data type, or ADT for short. An ADT is essentially the blueprint that tells us what can be done with the data, like whether we can add, remove, or find an item. It does this without getting bogged down in how the computer actually executes it in memory. It establishes this really clean interface, separating the data structure itself from the program that wants to use it. Moving on to section 2, linear versus nonlinear structuring data. So on one hand, we have linear structures, like an array, where data sits sequentially, right in a row. It's kind of like books neatly lined up on a shelf. Super easy to implement, sure, but it can actually waste memory if the fixed size isn't fully utilized. Then, on the other hand, we have nonlinear structures, like a tree. Instead of a single flat sequence, nonlinear structures build these complex hierarchical relationships. Think of a corporate org chart or your computer's file system, branching out from a root all the way down to various leaves. Let's run through some rapid-fire examples of linear structures. First up, a stack. This is perfectly represented by your code editor's undo button. It follows a strictly last in, first out, or LIFO principle. Imagine a physical, spring-loaded stack of plates at a buffet. You can only remove the plate that was most recently placed on top, right? When you hit undo on your keyboard, the software is doing exactly that, reversing the most recent action first, peeling back history one layer at a time. In contrast to that, a queue handles data just like callers on hold for a customer service agent. It uses a first in, first out, or FIFO principle. The very first person to call the hotline is the very first person served by an agent. Data enters at the rear and leaves from the front. It's a system designed to ensure everything is processed in the exact order it arrived. Now, as for our Tokyo flight question we asked at the beginning, we use graphs. Graphs map out non-hierarchical, physical, and logical relationships, which allows the software to connect dots across a massive network. Think about it. An airline flies between cities, connected by complex, overlapping routes. A graph allows the algorithm to instantly calculate the best path through that entire web of interconnected airports. It's pretty amazing. All right, let's jump into section 3, the rules of algorithms, the action plan. Now that our data is beautifully organized, we need action plans. An algorithm is just like a recipe in a kitchen, used to search, sort, or update our data containers. Technically speaking, it's a step-by-step procedure of instructions, executed in a certain order to get a desired output. And the real key here is that algorithms are conceptual. They are created completely independent of any specific programming language, whether that's Python, C++, or whatever else you might use. For an algorithm to actually be successful, it has to possess a few specific characteristics. First, the steps must be completely unambiguous, meaning they lead to only one possible meaning. It needs 0 or more well-defined inputs and 1 or more desired outputs. It absolutely must have finiteness, meaning it can't just loop infinitely until the end of time. It has to terminate eventually. And finally, it has to be feasible to run within the actual resource limits of your computer system. Oh, and like we mentioned, it has to be independent of code. When designing these rulebooks, developers choose from some really exciting paradigms to decide the core philosophy of their solution. For instance, will you use a greedy algorithm to just pick the immediate best option available right now? Or will you use divide and conquer to break a massive problem down into independent atomic pieces, solve them individually, and then merge the answers? Or perhaps you go with dynamic programming, where the computer actually memorizes past answers to overlapping problems just to save precious CPU cycles. Okay, that brings us to Section 4, Measuring Algorithm Efficiency, Time and Space. So, we have our containers and we have our action plans. But how do we actually measure their success? Well, we judge algorithms primarily on two major factors. First is the space factor, which is the maximum memory space they require to run. And second is the time factor, which is how long they take to execute based on the size of the input data. Now, a quick aside. We don't measure time with a stopwatch. Instead, we measure it by counting the number of key operations, like comparisons or additions, that the algorithm executes as the data scales up. Because this efficiency actively varies based on the size and shape of the input data, we have to analyze these action plans by predicting their best, average, and worst-case execution times. Now, while a best-case scenario is obviously great, software engineers are highly focused on that worst-case scenario, the absolute maximum time required. Why? To ensure that when millions of users hit the system all at once, the program won't just completely freeze up on them. And finally, Section 5, the Big O notation, asymptotic analysis. To seamlessly communicate these performance metrics, computer scientists use what's called asymptotic notation. Big O is a highly practical rule of thumb that focuses purely on the highest degree term of a mathematical function. Basically, we ignore the small coefficients and just look at the dominant growth rate to find the tight upper bound. In plain English, Big O tells us the absolute maximum time an algorithm will take as the input size grows infinitely large. It is our ultimate worst-case guarantee. Now, while Big O gives us our worst fears, omega notation bounds the function from below, showing us the tight lower bound. This represents the absolute minimum running time of an algorithm. It's our best-case scenario. It essentially tells us that, hey, the algorithm is going to take at least this amount of time to execute. And then, when we want the exact average behavior, bounded from both sides, both above and below, we use theta notation. This notation is specifically used when the worst case and best case time complexities actually grow at the exact same rate. This gives us a really precise, perfectly bounded look at the algorithm's overall performance. When looking at this ultimate cheat sheet of growth rates, you always want to aim high. A lightning-fast O of 1, constant time, means the operation takes the exact same amount of time, no matter how huge the data gets. Moving down the list, efficiency drops through logarithmic, linear, and quadratic times, all the way down to a sluggish O of 2 to the power of n exponential time. An exponential algorithm is incredibly slow, super resource-heavy, and is generally reserved for massive, complex recursive logic problems. Let's wrap this up. From taking chaotic data and gracefully structuring it into arrays, stacks, or nonlinear graphs, to perfectly measuring algorithmic efficiency using Big O notation, you now speak the foundational language of software. You understand the very architecture that prevents our digital world from just grinding to a halt. Which leaves us to wonder, armed with this knowledge of structured data and hyper-efficient algorithms, what complex problem will you solve next?